Our next speaker, Matthew here, has been quite regular at GopherCon India. The first time we were here, I embarrassed him because his fiancée was in the audience, and you're still happily married, I believe, right?
Yes, yes.
So I did my job well. Okay? And I always wanted to ask you, right? 2 years ago, you told me the craziest thing you did was roasting marshmallows
in a volcano.
On an active volcano. So any volcano since then?
No more volcanoes, no.
Metaphorically speaking. All right, let's talk about distributed time series and databases. You've gotten serious.
Yeah, serious
All
stuff.
right, Matt, go.
Totally serious. Cool. That's awesome. I'm hoping everybody's kind of woken up from the awesome lunch. It's like, just need some energy. I'm glad he kind of got the crowd started. I'm going to try to get this a little bit intense so that way like everybody wakes up. So today I'm going to talk about distributed time series in Go. And we kind of fell into this. We started just monitoring some systems internally, and we saw like the power of using Go as a time series database. And the talk today is going to be about how we started out from a single machine to monitoring about 1 million machines with Go. So I think what's really cool about Go is I think Go is the future of NoSQL and NewSQL databases. Like, if you see a lot of the new databases that are coming out are actually being written in Go. You're not seeing them being written in Java or C++ anymore. Like, we saw a talk yesterday by dgraph. So there's a graph database in Go. There's multiple time series databases in Go, Prometheus and InfluxDB. There's even a quote-unquote new SQL database called CockroachDB, which is supposed to be like Google Spanner. And of course, most people are using either etcd or consold for discovery, and they're kind of consistent key value stores. So we have 7 very popular databases being written in Go. So the future is very bright in this area. So today I'm going to really be talking about architecture. I'm going to talk about how we kind of took a lot of really basic building blocks, and we were able to scale up to being able to take in metrics from millions of machines from just kind of really off-the-shelf building blocks. And we're also going to kind of dive into like how we store data and how we optimize our storage systems. So how many people here use a time series database in production? Like 10 people raised their hands. I don't believe that, because you're going to have to talk to me afterwards. If you have monitoring and metrics on your production systems, which everybody should, if not, I'm going to come after you, you are using a time series database, most likely. So kind of what is a time series? Like, most people know the example is a stock ticker. So this is one of the indexes here in India. And basically what makes a time series different from a regular database is that it's over a period of time, which is obvious. But basically it means that we have single points at single points in time. And what does that actually look like? It means that we have a key, a timestamp, and a value. And a key and a timestamp and a value. And that's pretty much the schema for an entire time series database. It's very different than something like MySQL, where you have like maybe different columns and different tables. Time series are very just what happened over this period of time. And there's lots of really cool use cases for it. So like, I used to work in fintech, and we use time series databases for everything. And one day, we were monitoring our CPUs. This is at Bloomberg. And we were like, oh, wait a second. CPUs are just time series. Why don't we just make stock tickers, which are the CPUs on our servers? So what we could do is all of our stock apps that we wrote, you could also look at the CPU or memory on all the systems. And it made me realize that everything is really just like a time series database. So what's kind of cool is time series have some really awesome properties I want to kind of talk about before we get into our architecture, is that time series can be lossy because a lot of times you're visualizing it, and the visualization doesn't need to have all the data points. So if you're looking at a year of data, you may only be seeing points at every minute. So you can lose data, or you can compress data at many points in a time series. Also, time series have very unique compression, because you can actually optimize the distance between each value, and we're going to kind of delve into like how we actually do compression inside of time series databases. And one of the biggest problems with time series databases is they're very write-heavy. So like, for example, on our system, we might get a couple hundred gigabytes of data written and maybe 100 megabytes read. So like the disparity between writes and reads is incredibly different. So to kind of start the story off, about 2 years ago, I started at DigitalOcean. And these were kind of really dark times for us for monitoring. We basically used every single monitoring product on the market. We had one team that was using Graphite. We had one team that was using InfluxDB. We had a team that built their own monitoring system that wrote data into MySQL. And we even had a 50-node OpenTSDB cluster, which if anybody knows OpenTSDB, that was like the biggest nightmare. My first happiest day was I got to turn off the OpenTSDB cluster. And like that was, somebody raised their hand. They were like super excited about that too. That was like really happy. So we were like, okay, we got to get rid of all these metric systems. We need to find one. So we started with this metric system called Prometheus. And all of a sudden we were like, oh my God, this actually works. This is really good. And this was like version 0.1 of Prometheus. It had just come out or something ridiculous. But we started taking each one of our internal systems and we replaced it with Prometheus. And we're like, this is really awesome. Like, so Prometheus is written in Go, and it's a single binary, and you install it, and it can scale up to monitoring like 1,000 machines. So we were really excited about Prometheus, and we said, man, could this Prometheus thing, like, actually, could we use this and monitor all of our customers' machines, too? And so we started to dig into Prometheus and see. So if anybody here, how many people here have actually used Prometheus before? Only a few people. Who here uses, like, InfluxDB? Nobody? Okay, that's 2 people. Who here uses something like Datadog okay. Not many metric systems. I'm curious that most people don't have metrics here. So the thing with Prometheus, though, is it's a single node database, right? It stores its data as key value pairs inside of level DB. So it can't really scale beyond a single machine. So that was kind of our first roadblock. We were like, okay, we want to take this kind of non-scalable piece that's incredibly fast, and we were like, how could we start to scale this up to start offering a service to our customers? What's kind of cool, so the other thing that Prometheus provides are this query language for metrics. And you can kind of do things like you can take the rate, or you can take functions over your metrics and do aggregations over periods of time. And it's funny, because I tell people about this a lot, and I say, this is really awesome. And they said, no, I think you should just use SQL. Why would we invent another language to query metrics instead of just querying using a SQL language? And I said, okay, well, you got to see this tweet. So there's this tweet, basically, it may be hard to see on the screen here, but basically, you have a metrics query, which is like literally 10 characters. And then if you were to write the SQL query, it would be like 10 lines of code with like 500 characters, and it would be incredibly difficult to debug. And this is why we actually don't use SQL as a dialect for our queries. So we started off and we said, okay, we're going to use Prometheus as our initial architecture, and we're going to offer a service to our customers. So we offer and sell virtual machines. So we wanted to give metrics and graphs to all of our virtual machine customers. So we said, okay, here's a beta for about 3,000 people. And how can we scale Prometheus to support maybe about 3,000 users, which is not a lot. So what we did is we took Prometheus and we did the simplest thing you could. We installed multiple of them, and we started doing these hash ringing. So basically, who here has used a consistent hash or is familiar with consistent hashing? Okay, like that table over there, there's like 5 people and the rest. So this is awesome. So one of the cool things is if you ever need to scale something, one of the quickest things you can do is you can use a thing called a consistent hash. And basically what you do is you just split your keys to like multiple servers. So what we did initially was we just took different portions of our metrics coming from different clients. So we would say like user A would go to server 1 and user B would go to server 2. But we would just use this thing called a consistent hash to determine which servers they would want to go to. And this is kind of the architecture. So we had a whole bunch of Prometheuses, and then we had a single microservice that would kind of map all the Prometheus shards together to kind of fake to being a database, right? And this was cool. So we were able to get this beta out. We were able to kind of get a lot of customer feedback about the beta. But one of the things that we really came out of the beta was we realized what our performance requirements were really going to be if we wanted to scale to 100,000 customers. So the next business requirement that came to me was, okay, this is cool. 3,000 users is cool, but we need to get at least 10% of our user base. So we need 100,000 users. And we were like, whoa, that's like a totally different scale from the 3,000. And we had to do things like scale up to like taking 3 gigabits of metric traffic incoming. And we needed to have about 20 terabytes of storage to store 100,000 users' data. So we knew that our initial architecture was just not going to scale up to these levels. So that's when we started working on this project called Vulkan. So Vulkan is an open source distributed time series database. You can download it now on GitHub. It's about 6 or 7 months old. Well, it's about maybe a year old internally. And it can scale up to 100,000 users. We have 100,000 customers, I think, now on it in production. So you can scale. Now, I will give a caveat that most people probably can get away with having a single Prometheus instance. If you have in the low hundreds of servers, you can probably still get away with just using a regular Prometheus instance. So when we started writing Vulkan, we were tweaking with Prometheus, and we said, how can we just take Prometheus and scale it upwards, right? So we started to do some small pull requests into the Prometheus server itself to like start fixing different features to help us scale. And we noticed that a whole bunch of other people were doing PRs that were exactly the same as us. And we didn't really think anything of it at the time. And one day, we were at a conference in Berlin. We were at the Prometheus conference. And we run into the Weaveworks guys. And both me and the guy from Weaveworks did the exact same presentation where we said that we took Prometheus and we've scaled it up. So we ended up getting together, and we started to talk about how we can actually take this open source project and build other components around it to scale. So it's not really a fork of Prometheus, but it's kind of an add-on to Prometheus. And now we're kind of going to get into the portion of like, what did we actually do to like scale it up? Is the first thing we started to do was we split everything into microservices. Like, I mean, there's been a dozen talks in the conference about splitting things into microservices. We moved everything onto containers, and of course, we deploy everything onto Kubernetes, with the exception of our databases. And we started to use message queues to kind of buffer in metrics. So we're going to dig into each one of these pieces here. The first portion of scale that we were having a problem with was inbound metrics. So when we started to ramp up our customers from 10 or 20,000 customers, we started to have maybe 1 or 2 gigabits of actual raw metric traffic a second. And we were like, okay, whenever we have like a hiccup in our database, we would actually just lose data. And we were like, how can we buffer this data in such a way that we can like handle hiccups and actually recover from it? So kind of what we did was we built these special microservices that wrote the data into Kafka. And if you're not familiar with Kafka, Kafka is a distributed queue. And Kafka stores maybe a couple terabytes of the metric traffic. And then we have a separate set of microservices that read from Kafka, and we're inserting into Prometheus. And this was able to like scale us up to the next level. So we were able to get maybe 10 or 20,000 customers just by being able to have some buffering and having some more Prometheus servers. And this was good. So we were slowly but surely able to scale up the system. The next part of it was scaling up the storage, because basically we wanted to be able to have longer retention windows, and we wanted to be able to scale how much storage we were storing. So to start off, instead of like actually building our own underlying storage system, we took like an off-the-shelf one, which was Cassandra. And basically, we've modified Cassandra to store our long-term storage. And I'm going to talk about, I want to dig into like how we are actually using Cassandra to store the metrics data. So if we come back, and we talked earlier about what does a metric actually look like. So this is kind of the representation of a metric. You have a key, you have dimensions, which are labels. So like a single HTTP request could have very many different status codes, or could have very many attributes. And then you have a timestamp, and then what the value was at that point in time, right? So it's conceptually very simple. So what did we do? We just built a single table that had 3 columns. And we said, cool, we're going to build a table that has 3 columns. You can have a key, you have a timestamp, and a data point. And this was awesome. And we started to write into Cassandra at like 100,000 writes a second. And we were able to scale to maybe like 30 or 40,000 users. But then we started to get to the point where we were just running out of I/O in Cassandra. And it was just not possible to like scale from this level. And we kind of wanted to step back, and we said, how can we actually like compress the time series data in Cassandra in such a way that would actually be able to store much more and have a lower write throughput? So we went back and looked at how Prometheus actually stores metrics. So instead of trying to store metrics as single points, you create these chunks. And basically a chunk is a 1 kilobyte blob with series of timestamps and values. But instead of just keeping timestamps and values, you do deltas. Because, for example, time is not going to change very much. So you start off at 10 seconds, you start off at like 5:36 and 45 seconds. Well, you're going to increment by 1 second. So instead of having to store a full timestamp, you can just store 8 bytes, which is, the next one is 1 second later. And things like numbers. So like if you were looking at a CPU graph, you can do things like, it's called delta encoding. So basically, if the CPU is at 100%, then it's at 99%, 98. You can just store 1, 2, 3 instead of storing 99, 100, 100. And you can basically go from using a 64-bit number for every single point in the time series to using 8-bit numbers. And then we even do things like we have variable bit encoding where we can even condense it lower. But basically, the idea is that we can use different kind of encoding formats into these 1K chunks, which was great. But one of the problems was, so we were able to take for every about 500 kilobytes, we were able to compress it down to 1 kilobyte. So it was like maybe multiple 100x reduction in actual size. But the problem was, because it was so efficient, we were getting about 4 hours of data in a single kilobyte, which meant that we were only writing to the database every 4 hours, right? So if you wanted to see data in between those 4 hours, we had to come up with like a solution kind of in the middle. And basically what we did was we ended up building an in-memory query engine. So we took the base Prometheus, and we store these chunks in memory. And we have about a terabyte of RAM on our Kubernetes cluster for the in-memory instances. And basically what happens is the in-memory instances keep these chunks in memory for 4 hours. So that way you can still read it. And now what we have is a microservice that reads first from the in-memory chunks on the different servers. And then beyond 4 hours, it goes and grabs the chunks from Cassandra. And then we merge them together, and that's how we were able to like, then now we're at about 100,000 users on the system with being able to do these kinds of optimizations. And next, we're kind of working towards 1 million. So some of the cool things is now that everything is in containers and it's all deployed, is now if you want to add in different features, like for example, downsampling. So with a time series database, after about a day, it's not that useful. You don't really need 15-second resolution after a day. So you want to do things like you want to take 15 seconds and you want to convert it to a minute. So that way you're saving 5x your storage. So what we do is we just have extra containers that spin up, read the same old data, and write new chunks. And these chunks have less data points in them. And it ends up being 5xing our storage. And what's cool, and then also we wanted to add in more features. Like, so for example, now we offer alerting to customers. So like if you're having high CPU on your node or these things, we can alert on it. And what did we do? We ended up spinning up new microservices that consume the Kafka bus, and in memory, keep the time series in memory and create alerts from that just in memory. So we're able to kind of reuse this bus pipeline to reformat or recirculate data throughout the time series database. So I want to just show kind of the final architecture, or not really the final architecture, but the architecture that we're at now, where we have, and this is hard to see, but if you see the slides, you'll see it. Basically, we have all of our different data centers. We have customers, virtual machines, and all these data centers that are pushing metrics into a single set of microservices. And these microservices are basically just transforming that data and storing it in Kafka. We also have some authentication microservices that use MySQL, but that's pretty lightweight. Once all the messages are in Kafka, then we have very different microservices that are running inside of Kubernetes. We have one for alerting, we have one for downsampling, we have one for backup, and we have one that writes to Cassandra. And each of these microservices is basically just keeping a feed of Kafka, and we can add in new value-added services at any point from the Kafka. And basically, we're just storing the data in Cassandra, and then we have another set of microservices that read the data and offer gRPC interfaces to our web teams. So this is kind of the end architecture that has allowed us to kind of get to 100,000 users. So a couple of the things that I will note is some of the architecture is still using some Java-based tools. And I saw some really interesting talks yesterday about the dgraph, and what I'm going to experiment next with is seeing if we can replace some of the Cassandra bits with actually using like Raft or some other distributed database, so that way we can actually do the storage underlying inside of our own microservices instead of having to rely on Cassandra for some of the storage needs. And with that, I'm going to open it up for some questions.
Hello. Yeah. Hi, this side. Hello.
Yeah.
Yeah. Hi. So you just showed in the architecture. I see that there is a metrics column. Exactly, the metrics microservice. Now, in the previous slides, also you showed that there was an HTTP request total metric that was being stored along with the time series and the value. The question is that how in this architecture can writing new metrics be included?
Right, so the question is how are new metrics included? So basically, the HTTP API to post metrics allows any arbitrary metric names and any arbitrary fields on the metrics. So the clients can just add new metrics as they want.
So individual clients can themselves contribute to the metrics and sort of analyze it on the dashboard. Is that what it is?
Right. So, for example, we have a virtual machine product and we have a load balancer product. The load balancer team added load balancer metrics into the system, and we didn't modify our backend at all. They just started pushing in load balancer metrics.
Sure. Thanks.
Hi. What's the impact of reconstructing the time series data of the chunks? Because when you're going to present it back after a read, you'll have to do some computation for that. It's not ready for use immediately, right?
Right. Yeah, so that's actually a really good question, is how do we actually recombine it? So basically, this one microservice is reading it from Cassandra, but they're in giant chunks. So I mentioned that a chunk could be 8 hours of data or 4 hours of data. So if somebody requests, let's say somebody requests 2 days, we have to grab maybe like 30 chunks of data And then in memory, we have to filter down what portion of the metrics that person actually wanted to see, and then return it. So on the back end, it might be reading a couple hundred megabytes of data potentially in a query, but then it comes back to the client as maybe a couple kilobytes to the web front end.
Hello.
Yep.
Hi, nice talk. I have actually two questions. So first of all, you have replaced the storage engine with your in-memory storage and the Cassandra.
Yep.
And you have built a query engine on top of your in-memory memory metrics, which also does alerting. So you have kind of reused a lot of bits of code of Prometheus and Alert Manager for doing a lot of these things, but where are you using Prometheus?
Right, so that's a good question. Where are we using Prometheus? So basically, if you look at the source code to Prometheus, they have a storage layer. And basically, we're replacing their storage interface, but we keep their query interface. So what's awesome is we didn't have to build a query language or a query parser. We use all of the query analyzers and optimizers inside of Prometheus, and then it pulls into either our in-memory store or our Cassandra store.
Okay, and the second thing is like in your in-memory or the Cassandra store, the metric key has all the metric name as well as the different labels.
Yeah.
So how do you optimize or query, have queries which has labels as star, like you may have
Oh, yeah, so that's a good question. So what happens when I showed this one before, that you can have multi-dimensional queries or metrics, where a metric can have different attributes? And he's asking, how do we actually search on that? So we actually, I skipped over it because I was a bit low on time, but basically we have a table that keeps, it's a kind of a prefix lookup, and we basically keep an index table of the prefixes to the metrics, so that way we can find out all the available attributes that a metric will have.
So that is where MySQL comes into picture.
No. So this is actually another table inside of Cassandra that is actually storing this data. The one downside of using Cassandra is every single type of index you wanted to make, you have to make new tables that store the indexes, and you have to manually build your own indexes.
Okay, thanks.
Okay.
Hello. Yeah, Matthew. So does it fix Prometheus's cardinality issue? Can you scale cardinality as much as you want here?
Yeah, so does it fix the cardinality issue? Yeah, it definitely fixed the cardinality issue. And for those you don't know, is that the problem is with Prometheus is because the way it stores its indexes on disk, if you have something like Kubernetes where you're constantly refreshing the names of things, you can sometimes blow out the cardinality and reuse too much disk. Yeah, so since we're using Cassandra and we're doing index prefixes, we can actually pretty much go somewhat infinite on cardinality. So that problem is solved, yeah.
Okay, if there are any more questions, catch Matt later on. But thank you so much, Matt.
Cool.